Hello and welcome back to Calculus 1 for one last time. Right? This is it. U-substitution part 2. We are going to finish off the U-substitution. Now we're going to talk about definite integrals and back substitution. And that will conclude Calculus 1. So we talked about the U-sub in its pure basic form, where we said that we are supposed to look for function derivative pair and then substitute function with u and then use the derivative part will become du. You have the substitution there. If you have to fix constant, you do that. And then you move on. It's a backwards chain rule, and as integration technique, the most used, most frequent technique there is. So now, as we go, we are going to take a look at the u-sub in definite integrals. Right, so definite integrals are very frequent. Actually, entire Calculus 3 is definite integrals only, pretty much. So you are going to see a lot of definite integrals, and you know that the definite integral has limits, a to b, and I have to start by writing this down. If you have integral f of x dx, the limits are x1 and x2. So all of the variables inside the definite integral are x variables. It's x variable in the function, it's x variable in dx, and it's x variable for the limits. So when I write those a and b, I mean x1 equals a and x2 equals b. So now I hope you see that when you do u substitution, you are not only going to substitute u in a function and du, you will also have to transform limits. Because as you go on and you create your u-substitution better be u1 to u2, and then some kind of function g of u, and then du. So all variables have to switch. Now, the transformation of limits is actually going to be very easy, because all you're going to do is you're going to plug in lower limit and then upper limit one at a time in your u-substitution equation. So let's do the most basic example. Let's say you have to work on the integral of, this is going to be a very simple thing, integral of e to the 3x dx, and your limits are 1 to, let's say, ln 6. All right? So this is a definite integral. Now, you know how to solve this problem if you don't have limits, and you do the same. So your u is what? What's u? 3x, okay? And what's du? The derivative, which is 3 dx, right? Oh, actually, wait, I don't want ln 6 here. Let's just go 1 to 6. 1 to 6. Just erase the ln. We'll do ln in the next problem. So now I have this, and then what I do is I have the integral. You know that you have to fix the constant, right? You need a 3, and then you need 1/3 in front. So now we have 1/3 e to the u du, and it's time to switch the limits. Now, I'll do that in blue. u1 is 3 times 1, which is 3. So that's the bottom limit, 3. u2, which is the upper limit, is going to be 3 times 6, which is 18. And the upper limit is now 18. Note that this new integral is entirely in terms of u, and your limits are also u. Therefore, we are not going to switch back to x at all, because we are computing a definite integral, and you have all of the variables to be u. So we have now 1/3 e to the u computed from 3 to 18. So we are not switching back to x because we have our limits to be u, and you're just plugging in u for u. So it's 1/3 e to the 18 minus e cubed, and that takes care of this thing. I'm not going to compute the thousands. They're there in the answer. No one cares. This is the exact answer. Done. Right? Now let me go and see if we can make. I said I'm going to do something with ln, but I actually have a better idea. So how about this? We go with the integral of the cube root of cosine squared x sine x dx. So this problem already looks terrible. And we are going to go from pi over 4 to pi over 3. This is terrible, right? Well, if you rewrite it, it will look immediately less terrible. If you just go integral pi over 4 to pi over 3, with the cosine of 2/3 x sine x dx. And you immediately see that the function derivative pair is cosine and negative sine, right? So u is going to be cosine x, and du is going to be negative sine x dx. Now I don't have that negative, so I'm going to fix that now. I put the negative in front of the integral, negative inside the integral, and I have those. So now let's go and have the negative integral of u to the 2/3 du. Oh wow. All right, nice. But now I need to transform these limits. Remember that my original limits are x1 equals 2 and x2 equals 2. Now I need u1 equals 2. We take the original limit, which was pi over 4, and we plug that in the sub-equation. So that's going to be cosine of pi over 4, which is root 2 over 2. So new limit is root 2 over 2. And the u2 is the same deal, where I have cosine of pi over 3, which is 1/2. So that's the top limit, is 1/2. So we eliminated everything. We eliminated pi's in the limit, and we also eliminated trig. Right? The entire problem now is going to be very quick. We have negative u to the 5/3 over 5/3 computed from root 2 over 2 to 1/2. So this is negative 3/5, and in parentheses I have 1/2 raised to the 5/3 minus root 2 over 2 raised to the 5/3. This answer is exact. If you want to punch this in a calculator and you put 17 decimal number, go ahead, waste your time. But in my opinion, this is good enough, right? I have exact answer over here, and problem in my humble opinion, which is rarely humble, but that's that, is over. That's exact answer. So if you're when you're looking at this problem, you are starting with trigonometry, with the cube root and pi limits and all of that kind of stuff, just to condense into this, which is a polynomial-like. It's not a polynomial, but it's a polynomial-like calculation where you just have u to the n+1 over n+1, which is obviously easy to deal with. So when you have limits on your integrals, you will have to transform those from x1 and x2 into u1 and u2. And if you have a definite integral, you do not have to go back in the x domain. Now, some students that think, for whatever reason, or should I say delusion, that this is difficult of plugging in two numbers in equation that you already have. Those students do not transform limits. What they do is they solve the problem, and then they plug back x formula, and then they use the old limits, which is much longer and more work than if you do two simple calculations on the side to change those limits and go directly into your answer. You will also see that once you move to Calculus 2 and you do trig substitution, you really do not want to go back to the original problem, fighting your ways through inverse trig functions and other things. It is much easier if you transform your limits on step 1 and then just quickly be done with it. So do yourself a favor and just use the sub-equation that you always have. Every problem we did today had the u equals something there. Just use that equation to transform both of your limits. And then, now there's one more thing that it's, the cool fact is that in some cases it will look weird because you are going to end up with a bigger number in the denominator and a smaller number on the numerator. The bigger number in the lower limit and the higher number on the upper limit. But we have the formula that says you can swap them and then you get the minus in front. Or if there is a minus, it disappears, right? So you have that. Also, if you don't switch them, well, it doesn't matter because it's going to be upper limit. It's not higher number minus lower number in a theorem. It's upper limit minus lower limit in a theorem. Right, fundamental theorem calculus. So even if you don't switch them and you compute with a smaller number in the upper limit, it will still be the correct answer at the end. So it doesn't matter. So just, you need to know if there is a situation like that. The last part of this lecture is this back substitution. It is very rare. But it pops up from time to time. As I said, only one problem in my Calc 3 so far. It happened, I believe it's yesterday or no, not yesterday, 2 days ago. And one of the students who's, clocking 100 on every exam said, oh, I completely forgot about that. So it's called back sub procedure. Here's an example. Integral of x square root of x plus 1 dx. So this is like a standard example. There are some variations of it out there. So you're looking at this and you say, well, this x plus 1 is really evil, right? So clearly that's going to be your u sub. And do we all agree, like 100% of us agree immediately when you look at that x plus 1 is the u? It should be obvious, even at this stage. So x plus 1 is there. And then your du is equal to 1 dx. So du is equal to dx. You see, but hell breaks loose when you try to substitute because there is that extra x in front, right? And you don't have it. Now you can't work with the variables the same way you work with constants and just say, okay, let me divide by x. And no, that doesn't work. Only works on constants. So as you start substituting, right, leave some space, you definitely have a square root of u du, right? And now this is an issue, right? You can't have x there copied. So what do? Well, you solve this equation. So this is what's new. You solve this equation for x, and that's going to be u minus 1. And that's what goes here. That's why it's called back substitution. And now if you look at this problem, you can distribute square root of u, and you will have u minus 1 times u to 1/2 du. And I'll just say distribute to get integral of u to the 3/2 minus u to 1/2 du. And now this becomes a basic problem because you have u to the 5/3 divided by 5/3 minus u to the 3/2 divided by 3 and then half and then plus c. Clearly bring x plus 1 back. So that is equal to 3/5 x plus 1 to the 5/3 minus 2/3 x plus 1 to the 3/2 plus c. And this is what we have as our problem. So now that you see the entire problem, the issue was that x in front, and the reason why it's called the back substitution is that we actually had to go back to u sub and solve for x and plug in. You are going to run into this maybe 5 times in your education, okay? So it's very rare, but there is no other way to solve this problem. So you either can do this or you can't. The last problem that I'm going to solve here is not the u sub problem. This is a problem that can only be solved if you know a certain trig identity, and this is now going to turn into that 5-minute talk on what to work on if you want to have a comfortable Calculus 2 class, right? Most of you have heard that Calc 2 class is hell on earth, and yes, it is going to be hell on earth if you don't have prerequisites for it, if you don't have a preparation that the class requires. So if you are looking into a problem cosine squared x dx, the integral of cosine squared x dx, now this particular problem is not the basic integral because of a square, but it's also not u substitution because there is no sine x for our du part. So none of these techniques work. And the only way to solve this problem is to know the reduction of power. So they're called power reducing formulas in trig. You learned this in Calc 2, in pre-Calc 2, where you know that sine squared x is equal to the 1 minus cosine 2x over 2, and that cosine squared x is 1 plus cosine 2x over 2. So using that formula, this becomes 1 plus cosine 2x over 2 dx, and then this splits in two integrals, integral 1/2 plus 1/2 cosine 2x dx. And now the second integral there with the cosine 2x is a u sub, but you also memorize that you can just divide by that 2, right, when you change it into a sine. So this works out to be 1/2 x plus 1/2 sine 2x over 2 plus c, for a total of 1/2 x squared plus 1/4 sine 2x plus c. And this is it. This is what we have as the answer. There's no other way to solve this. There is no u substitution you can do. There is no any kind of magic other than knowing this. So knowing these formulas is a must. Now your Calculus 2 class is going to be broken into two parts, two major parts. First part, chapter 6 and 7, and they're all integration. And then chapters 8 and 9, they're all sequences and series. So the first two chapters will be integration, where pretty much every single integral you see will end with u substitution. And then the second two are sequences and series, which every problem is a limit problem. So for Calc 2, and here it is spelled with K's, we need 2-point sections 2.3, 2.4, that's the vertical asymptotes, I'll explain that as well. We need 4.7. All of these sections are limits. We need 4.9, 5.2, only the calculation part, not the sums, but yeah, sums, and then 5.5. And this is your integration. Do yourself a favor and know these sections forwards, backwards, from the middle, backwards, from the middle up to 3/4, right? So no matter where you are in that section, know everything from these 6 sections. In addition, you need, so plus trig identities. And you need the ones that I'm going to write. Clearly more is better, but ones that I write is a bare minimum, and you have to know. So all 6 trig setups, and I'm just going to write one. Sine of theta is opposite over hypotenuse, and I'll put 3 dots here for the other 5. You need to know all of them. Then you need to know that tangent x is sine x over cosine x, and that the cotangent x is cosine x over sine x. You need to know that the secant x is 1 over cosine x, and that the cosecant x is 1 over sine x. Further, you need to know the power reducing formulas, or you are doomed. So that is sine squared x is 1 minus cosine 2x over 2, and cosine squared x is 1 plus cosine 2x over 2. Pythagorean identity. Pythagorean identity actually has, if you are also counting when you flip them around, has 9 flavors. So sine squared x plus cosine squared x equals 1. And then you also, if you divide everywhere by sine, you get by cosine, you get tangent squared x plus 1 is secant squared x, and 1 plus cotangent squared x is cosecant squared x. So those, right, are necessary. And then you have the double angle for sine. So sine 2x is 2 sine x cosine x. And we might toss in the cosine squared, but the cosine 2x, but that's not as necessary. So generally, I don't write it, but cosine squared x minus sine squared x. These are the trig identities that you will use. And the last chapter of Calc 2 is going to be chapter 10, where you learn parametrization and polar coordinates and calculus in polar coordinates, and those 3 or 4 sections are your preparation for Calc 3. And technically, if you don't you have to know all of those sections to actually even survive anything in Calc 3. So this is your prep for Calc 2. I would suggest strongly, if you are taking Calc 2 in a second 6 weeks of the summer, to spend a lot of time over those 10 days between the 2 semesters to go through those 6 and make sure that you are at least familiar with these trig identities, and then you will, right, as you practice them and see them in problems, you will be there. Now, if I have to single out some stuff, then definitely, things that you will use most of the time are these in Calc 2. That's pretty much most of your trig dealings. You'll see everything else, obviously, that's why it's on the list, but, you know, most of the time are these guys. And that's your prep for Calc 2. I also encourage you to go into, you can also go on my channel and look for the first lecture of a Calc 2, where I go through the all of these in details and do some proofs and some review from Calc 1. Derivatives are not going to be a central part of Calc 2. They will show up, but not as many. You will have the length of the curve, right? And the surface area formula, they will have derivatives in them, but derivatives, you will have to take them obviously for u-sub every time, so yeah, they're pretty much in every problem, but you're not going to have derivative as the derivative that frequent. And then obviously chain rule, right? So that's the Calc2 prep. Let's restart the stream for final review and talk about that briefly. And that's Calc1. Fair?